Hello and welcome to another Solana tutorial. Today we're gonna talk about the Solana kit again, and specifically we're gonna have a look at signers, how signing stuff works with the kit. Because on first glance that seems a bit counterintuitive and complex and confusing, but once you understand it, it's actually really nice. So today I want to just focus on signing with the kit. And really, I'm making this video because I found this answer promoting the kit. And look at that. That's the logo. And I've never seen that before. The kit is, what is that, a fox? Are you supposed to be a fox? Something like that. That's the logo for the kit. Never seen that before. So here we are looking at the kit. Solana kit. And in here they introduce solanakit.com, which is basically a website with docs. And those docs I've never seen before, and I wanted to show you that this exists. That's the main reason for making this video. And in here you can find all of the basics, how to get started, how to send a transaction, a deep dive on codecs. We did make a video on codecs before, but in case you want it more like with text and stuff. Those docs are really well written. I enjoy them. And today we're gonna have a look specifically at signers, because that we never really looked into. We've been using them, but today let's deep dive. Signers are an abstraction that combines an account with an implementation that computes signatures on behalf of that account. I mean, yeah, that makes sense. If you think of what is a signer in the context of Solana, we always sign for an account, so that has an address. So a signature always corresponds to an address. And in order to sign for that account, there is some specific implementation, however that implementation looks. And the signer really is just the interface. It's the abstraction that combines account address and implementation. That's really what it is. So in practice, that implementation can then come from a wallet app, like a browser app that you use to sign with, a network API, calling some endpoint that provides the signature, then the local crypto API, or a user space implementation, your own implementation that you use for creating the signatures. So that's the signer interface. You can use it with the kit. The kit's signer aware functions. So you just need to plug in the correct signer and the kit will be able to work with it, is essentially what it says. And that makes it easier to build, sign, and send transactions. Okay. Installation, there's a separate package, Solana/signers, but it's included in Solana/kit. But if you just need the signers, that's in here. And there we go. All signers are wrappers around an address, because an account has an address, and the address is the thing that defines the account, and therefore every signer must have an address. And so that means whenever we require an address, it might also accept the signer. Each specific type of signer has one or more capabilities, such as the ability to sign a message or a transaction on behalf of that account. Some even add the ability to sign and send the transaction, which is common for browser wallets or phone wallets. Okay, because they don't want to give the signature to the API for security reasons. They want to send it directly to chain then. Okay, so that's an example. But before we go there, let's check the type of signers, because there are 3 categories and 2 types of signatures, which gives us 6 total, but really it's just 5 different signers. 3 of them signing transactions and 2 for message signing. So the 3 categories are partial signers. They're just used for signing without modifying the transaction or message. Then there are modifying signers, which can modify the transaction or message, which obviously invalidates any pre-existing signatures. And then there are sending signers. They can also modify the transaction, but they will send it at the same time. So this category doesn't apply to message signing. This is just for transactions. So in this neat little table, we see we have partial signers, modifying signers, and sending signers. both for a transaction signer and a message signer. So we have the transaction partial signer, or the transaction modifying signer, or the transaction sending signer. We've heard those names before, but now we can make the connection what that actually means. And then for message signing, which we don't do as much, there's the message partial signer and the message modifying signer. So let's go through them. The partial signer for a given address, like all the signers, has the address and the implementation for signing transactions, which takes an array of transactions and produces an array of signatures, or a signature dictionary, which is the address and signature pair. There, we see it even here. For an address, we have signature. It's a dictionary. And that contains the actual implementation in here. That's just the interface. And if we have an implementation, then we have an actual transaction partial signer. Characteristics of this partial signer: it returns a signature dictionary for each of the provided transactions. Oh, that's why we have the array. For each transaction, that's why this is also an array. Because the dictionary, for one transaction, we just need one dictionary. That makes sense. Without modifying them. So that's why the partial signers can run in parallel, because they don't change the transactions, so it also doesn't matter which one is first. So flexible order, since we don't change them, it doesn't matter in which order they're signed. Now, modifying signers, they also have address and they have modify and sign transactions. So it's a different name. This again takes an array of transactions and will produce an array of transactions with size limit and with lifetime. So here we're not getting the dictionary back anymore, but we're getting transactions again, because the modifying signers, guess what? Modify transactions, or can modify transactions. Therefore, the modified transaction somehow needs to be returned. And the transaction itself then contains the signatures again. So the signatures that are created in the sign, they are stored inside the transaction. It's not just the dictionary that we get back for the signatures, it's the entire transaction. Okay, those cannot be executed in parallel because each call can modify the provided transactions. And it says the provided transactions. So theoretically, it's not just that it can modify the transaction that it's signing, but it can modify the entire array of transactions, meaning it could add an additional transaction. It's not given that this array is the same length as it could modify the whole array, which is also new to me, but that's what the docs say. We can try this later. Another characteristic is that modifying signers are first signers. So for a given transaction, the modifying signer must always be used before the partial signer, as it will likely modify that transaction, thus impact the outcome of the partial signer. So if you have a partial signer and the modifying signer needs to sign first, obviously, because it changes the transactions. And when it changes transactions, then obviously the signatures that are already there are invalid. So we first want to use modifying signers and then the partial signers. However, if there are more modifying signers, which there can be several modifying signers, the second signer may invalidate the signature of the first one. If both modify their transactions, then we will get a conflict. However, modifying signers may decide not to modify a transaction based on the existence of signatures for that transaction. So they might check, hey, is there already a signature present? And if there is, then I don't modify the transaction because I know that would invalidate that signature. Depends on the custom signing logic. Maybe the signing logic really needs to modify it, then it will just do it and invalidate the signature. And then you gotta deal with that later. But yeah, that's the risk with those modifying signers. And then we still have the sending signers, which are like modifying signers, except that they also send the transaction. So it's a sign and send transactions. So really, they could have named it modify and sign and send, but that's a bit of a long name, so it's just called sign and send, which again takes an array of transactions and here provides the signature bytes, because we're not returning the modified transactions, we're just returning the signatures, because the transactions will be sent anyway, so they can't be changed anymore anyway. Can't really do anything with them anymore. But yeah, that's interesting that we don't get the actual transactions back anymore, so we can't even see what the transaction sending signer modified, we only get the signature bytes. Okay, this is a single signer. Obviously, there can only ever be one transaction sending signer because you can only send it once. And trivially, this must also be the last one because once you send it, no other signer can sign anymore. Like, this should be the last thing that you do. So first modifying signers, then partial signers, then the transaction sending signer, because that will actually send it. So yeah, and that's why we can also just have one of them sending it. And same as with modifying signers, we have the potential for conflicts since the transaction sending signer may decide to modify the transactions. And here it again sounds like this one can't add transactions. When I read this here, it felt like it can add transactions. For given transactions, the modifying sign must always be used before the part. I guess that's one thing that we gotta have a look at. Maybe I was wrong with it can change the array. Maybe it just changes the transactions. It enables to inject additional instructions to the transaction. Potentially modifies the provided transactions. So it modifies the transactions, not the transaction array. Okay, I misinterpreted that. We do just modify the transactions and not add additional transactions. Although maybe we can. That's one thing that we gotta try out. Okay, anyway, sending signers, we can have conflicts. Potential confirmation. Whilst it's not required by the interface, it's also worth noting that most wallets will also wait for that transaction to be confirmed, typically with the confirmed commitment, before notifying the app that they are done. So since that's async, that might wait for confirmation of the transaction before that returns, but the interface doesn't require that. It could just give back the signatures and then you have to confirm them yourself. So it depends again on the implementation. Okay, and for message signing, same. There's a partial and a modifying signer. But since we rarely sign messages, transactions is the more common use case. Let's look at that. And now we come to the actual implementations. So this was just the interfaces, right? Where it says the custom logic goes here. Now for the actual signers, there is a no-op signer that we can create with a create no-op signer for an address. And this will basically do nothing when it produces a signature. So why can that be useful? Well, for testing purposes or for providing a signer where we cannot currently sign, but when we then serialize the transaction or whatever. So for instance, if you need to send the transaction to a server that will sign and send it for us, then we can just work with a no-op signer first. So the no-op signer, we use it basically for the kit to be happy that there is a signer present, but when it actually calls the sign, then the no-op signer doesn't do anything. It's the same as having this as a literal implementation, where the actual implementation is no line of code and just does nothing or returns the exact same thing. Here it would just return the same thing. That's a no-op signer. And here it would just return a dictionary of zeros. That's the no-op signers. And then we have the key pair signers, which is the ones that we're using when we work locally, when we have the key pair available because we loaded from a JSON file or we generated a key pair with this generate key pair signer. And this then here, this is how you load it from file. This is how you generate it. Yeah. And then you can use the key pair signer because that will have the implementation for how it can sign. Okay. Maybe let's just look at that in actual code. Okay. PNPMI. Should we install the kit or just signers? Let's do Solana signers and import from Solana signers just to see what's here. I get bigger. Here we have all those things, the key pair signer, the message modifying and partial signer, the no-op signer, the transaction modifying signer, transaction partial signer, transaction sending signer. So those are all the transaction signers. Yeah. And all the functions to actually sign and the generate. Hehe, cool. So let's work with a no-op signer for now, just to see what we can do. And because we will still need to be able to await things, I guess I gotta do an async. There we go. And create no-op signer. And this needs an address. And I think address and stuff, that comes from the kit though. So it requires an address. So I will need to add Solana addresses. Yeah, why not? Let's do all the things modular like this. I mean, if I include the kit, then it will tree shake that anyway. But just so we see where it all comes from, let's also add addresses. And then we will probably also need transactions, but we'll get there. So address, what's in here? Codec. Let's say this was my address. Basically this, just with that actually exists on DevNet 8 days ago. Nice, people are using that address. It's a good address. Anyway, it's not one that I can actually sign for, but I can create a no-op signer for it. Eddie, I'm gonna call it Eddie because Andy address. So my Eddie is this, I put the Eddie in here, and then I have a no-op signer. And with this no-op signer, I can sign messages and transactions. So the no-op signer implements both message and transaction signer. So the no-op signer is a message partial signer and a transaction partial signer. That's why it has both of those implementations, right? That's why we can sign message and transactions. You know, back here, a no-op signer implements both of these. Okay, so anyway, and it has the address, so we can get the address out. That's the trivial thing. And then we can sign transactions, or we provide the transactions, and we get back a signature dictionary actually. Wait, so it's not a modifying signer then. Hold on, did I get that wrong? Oh, partial signer. Partial signer. Sorry, I looked at the wrong. Those two, it implements those two. The no-op signer, obviously, because it has no operation, doesn't modify the messages or transactions. Therefore, it's a partial signer. So, yeah, it's a partial signer. And as we saw, the partial signers, they, when we sign, return us the signature byte. So those dictionaries. So that's a signature dictionary array that it returns here. And a signature dictionary array, if you look at it up close, it's a record of address and signature bytes in an array. So a dictionary is a record of an address and signature bytes. Okay, so I guess to be able to work with this, we need transactions, transaction message bytes, and signature map. Gonna borrow this code here. Where does all of that live? This is actually in signers. The set transaction message fee payer is in signers. Where could that live? It's all in the kit, but obviously maybe some transaction. I don't know, I'll just add the kit. Then I can import this and this. So I'll put my no-op signer as the fee payer, and then that's my message, which has which type? Could I already put this here? No. But what I can do is sign transaction message with signers to get a signed transaction, because that will then internally call the no-op signer signed transaction with the correct bytes. So this happens in here because the kit handles how that's done, like which signer should be invoked first and so on. And let's look at this. Extracts all transaction signers inside a provided message and uses them to sign it before sending it immediately to the blockchain. Wait, this before sending it, that's already the next one. That's already this one. Here we're still in this. It uses them to return a signed transaction before asserting that all signatures required by the transactions are present. And the partially sign and send extracts all transaction signers in the message, uses them to return the signed message. It first uses all transaction modifying signers sequentially before using all the partial signers in parallel. So here we see it. That's how the implementation does it. If a composite signer implements both interfaces, it will be used as a transaction modifying signers. Otherwise, it will be used as a partial signer. Interesting. So if it has both, then it will be a modifying signer if it would be the only modifying signer, and if there's already another modifying signer, then it will be a partial signer. Interesting. Note that this function ignores transaction sending signers, as it doesn't send the transaction. And this one actually interesting. This one asserts that all the signatures are present. So basically, signed transaction message with signers is partially signed transaction with signers and then assert that all signatures are present. So let's see if that would even work. Let's log signatures. There we go. No, it does not work. Transaction is missing signatures for an address, Andy. Because even though the no-op signer is present, it doesn't really sign. So the check if it has all signatures will fail. So here we're not supposed to use the signed transaction message with signers. We're supposed to use the partially signed transaction message with signers. That way, we skip the check. And yeah, what we get back is the dictionary of this address, the Andy, has the following signature, null. There is no signature for this address. But I'm pretty sure that the no-op signer signed transactions has been invoked. And in order to check that, let's, instead of the no-op signer, create our own signer. So let's do a Andy's signer that will be a transaction partial signer. And we're missing the following properties. Add missing properties. There you go. I think I could even put the address here. Let's make it a function. And that returns basically this. So it returns a transaction partial signer, and I call it create Andy's signer. There you go. It's a function now. I create Andy's signer that I give the address, and it has the signed transaction. That all it does is it will say signer has been invoked, but it will not actually sign anything. We do need to return that signature array though, so I will need to return something. I will need to return an array of address now. And it's a promise, so maybe make it async. There you go. And then does not exist in type. How about this? An empty signature dictionary. So we're not even given the address in here, although I can try. That could even also work. Look, we just force it to say, hey, this is a signature dictionary. Trust me, bro. And then I call the same thing, except now I create myself an Andy signer, create Andy's signer for that Eddie, and then we use the Andy signer in here, and then now it uses the Andy signer and it adds address. So that's not the correct thing. Hold on, forget this. This is BS. This was already in here and it already creates this array or this dictionary for the signatures, and it will change the ones that the partial signer signed transaction adds, and if this adds nothing, then it doesn't change anything. So only if for that address, maybe the address that I put in there is not the right thing. Wait, because this is this. Maybe I would need to say, how do I get here? Wait, let's check something. Yeah, it has that thing. So how can I make a dictionary of that? I thought that's how that, but that's not how this goes. Then it takes the literal edit, which is not what I want. Can I deref that somehow? No, how does that, damn it. How do you work with TypeScript? Oh, that's the way, hold on. Like this? No. Conversion of type, string null to record, because that's a string. You have the wrong type. Convert it to unknown first. What if I provided actual bytes? There, I just can't provide null as a signature. But now check this. There we go. Now I have a signature provided for this address. The signature is now this, which is not a valid signature, but it is signature bytes. 3 out of 32. So that would work, right? This is how I could create a signature with a partial signer. Basically, I created myself a partial signer here, a transaction partial signer, that ignores the transaction and puts in a pseudo signature. Okay, cool, that's partial signer. Let's add a few more signers to my transaction, just for fun. Let's create another one with a slightly different address. 2, 3, and 4. 2, 3, and 4. And somehow I need to, because like this, obviously it's gonna still be the same. I need to somehow put them into the message, but I can only have one fee payer, so I guess I need to add some instructions that require signers. So let's do append transaction message instructions. Instructions, that's the message. And we will add, what's the simplest one that I can think of that requires, I mean, I could just create my own instruction, or I do a memo. Good old memo. Solana program memo, get add memo instruction. So we get add memo instruction, adding signers. And the signers, what's that? A transaction signer array. So here it requires transaction signers, but it doesn't say if it should be a transaction partial signer or transaction modifying signer or transaction sending signer. That's so cool. It just says transaction signer. It can be any of those. And then when we actually sign, then it will use them in the right order. That's so cool. So let's provide signer 2, signer 3, and signer 4 in here. So it has them as transaction signers. So when I sign the transaction message with signers, then it will take the implementations that sign for those, we will invoke that and add the signatures. So let's look what happens if I do this. Look, the signer has been invoked for 1, 2, 3, and 4. All of them were added. If I do that again, look at that. No, it's always the same. It's always 1, 2, 3, 4. But theoretically, that should run in parallel because they're all partial signers. So what if we await, because we are async, math random times, so a random amount of milliseconds, maximum a second should be enough. How does it look then? Look, then there we see that all of them are executed at the same time because this is now random. And obviously the result will always be the same because that's a dictionary that it will print in order again. But here, which one comes out first or which one is actually executed first, created the signature, that runs in parallel because that's now random, the order. If we execute it several times, then we get different results. Cool. Different orders. I like that. That's fun. So let's say that was my partial signer. And let's create a modifying signer, which should be a transaction modifying signer. Then this will be called modify and sign transactions. And it will also take different things. How about I use this? There you go. Then it gives me the correct things that it should return, like transaction with size limit, with lifetime, and so on. And then here, I'll let that wait exactly a second. And we will need to return something different because now we need to return the actual transactions. So can we just return the transaction? No. Transaction size is missing because now it's transactions with size. Damn it. So now we need to prove that it's within size limit and it must have a lifetime. This transaction doesn't even need to have a lifetime, but the modifying signer will need to add a lifetime. So with a modifying signer, you can't sign transactions that don't have a lifetime, it seems like, because they need to return it with lifetime. Which makes sense. I mean, this transaction that we're creating here, we couldn't really even sign it. Or no, we can sign it. We couldn't send it, like it's not a valid transaction because it doesn't have a lifetime. It doesn't have a block hash or a durable nonce or whatever. So it's missing the lifetime. So we can't do that. But set transaction lifetime using block hash. But I can't take that from the message bytes, no? That's already compiled. What I could also do is instead of adding it myself, being like lazy here and saying, hey, I just assert is transaction with block hash lifetime. Wait, I need to do this for all the transactions too. And then return tx. Because here it's a transaction or a transaction with lifetime. And here I assert that it's even with block hash lifetime. And then I get transaction with block hash lifetime. So let's say this modifying signer just allows transaction with block hash lifetime. Otherwise it would modify the transaction to have a block hash lifetime. But we're still not happy with that because... oh yeah, the size is still missing. Assert is transaction within size limit. If we assert that as well, there we go. Then we can return this. And now this is a transaction within size limit and the transaction stuff and a block hash lifetime. And that is then sufficient that I can return it. Yes, types, because we need all of that stuff. There we go. But that I can then return. I didn't add any signature. I didn't actually sign. But it's okay. For now, let's leave it like that. Let's see if that works. So let's add a signer 5 here. Let's call this modi. Signer 5, create a modifying signer and add the signer here as well. It doesn't matter where it is. The modifying signer doesn't need to be the fee payer, for instance. It is independent. Let's see what happens if we do this. Oh, an error. Extra length 33. Expected base 58 encoding address to decode by array of length 32, actual length 33. Oh, because this is one too long, I see. Okay, fixed it. There we go. And now transaction doesn't have a block hash lifetime. The assert fails I'm asserting it has a block hash lifetime. Perfect. That is to be expected because I need to add lifetime. So to this message, set transaction message lifetime using block hash. I'm just gonna use a pseudo block hash because it doesn't matter. I could query RPC, but I don't want to. But this also needs a block height. Last valid block height. Fine, there you go. This is made up. It doesn't matter what that is, really. I just need to give it a block hash lifetime. And with that, there we go. Now that works. And did you see the modifying signer was invoked first, sequentially, and then came the rest? Look again. First, just the modifying signer, then we wait 1 second, and then come the rest in random order because I still do random awaits. Nice. And I still have null for this because I didn't really provide a signature. How can I somehow fit a signature in there? That's gonna be hacky as well now, but like I want this transaction, the signature map. Could I be like, use this, but signatures... How did I do it up there? It's like this. This is a dictionary again. No, that's... Wait, signatures here is a signature map. Here it's a signature map, not a dictionary. But it's the same thing. It's again address to signature bytes. So I don't see why not. Let's do 456 here, just to see if that makes its way in. There we go. Here we go. So now I'm also providing the signature for this 456. It's not an actual signature, but it's a pseudo signature. There we go. Ah, that's so ugly. But still, it works. We have a modifying signer now. And now, while we're here... Wait, first, let's answer the question. Before we get to the transaction sending signer, let's answer the question that we had earlier of, could I modify those transactions as well? I don't think that I can, because if I would add another transaction, then here I would get more transactions back, and that just... No, I don't think so. But what would happen if I were to return 2 transactions here, for instance? Let's return that twice, maybe. What would happen then? Probably still... Let me think about that. Because on the one hand, it does make sense that if the modifying signer tries to add something to the transaction, but then the transaction becomes too big, then it might want to split that in 2 transactions. But at the same time, I don't think I want my modifying signer to be able to split transactions. For instance, if I have a lighthouse instruction at the very end of my transaction, I don't want that to get in a different transaction because that totally changes the behavior. So I don't actually think that modifying signers should be able to add transactions. Let's see. I've just been using the partially signed transaction message with signer. What if I use... Yeah, here it's always just one message. He's always talking about one message. So I can't... There's always one transaction. In this interface, here we can have several at once. Several transactions. I think what confused me when I read this cannot be executed in parallel, as each call can modify the provided transactions. The provided transactions, I think that was the sentence that confused me, or that made me think that it could, change the transactions. But no, each transaction can be changed, but we cannot add transactions. Because here we get a list of transactions, and each of them we should sign, and each of them we can modify, but we can't just mess with the number of transactions. It doesn't look like it because here I also just put in one transaction message and I'm expecting to sign it, so I'm not ever expecting this to come back as 2 transactions. So even if I return several transactions here, it will probably just take the first one. What if I do null as this? Trust me, bro, it got that. What if I do this? Yeah, then I don't have a signature for this one because it just tries to get it from here, and here I don't have a signature for this. And it ignores the others, obviously. Yeah, so forget that. That's just stupid. I gotta just return the same length transactions here. It doesn't make sense otherwise. Then I have this signature as well. Okay, so I'm like 95% certain now that I cannot just add transactions. That would be weird. Okay, and with that settled, let's look at the next thing, which is transaction sending signers. So let's create Andis sending signer and the missing properties. Now we have a modify and wait, hold on. Just because I changed that name doesn't actually change the type. I need to change this here. Transaction sending signer. There we go. And now we add the properties. Then we get this sign and send transactions, which again takes transactions and again returns just the signature bytes. It's so weird. Once it's returning a dictionary, once it's returning a map inside the transaction, and once it's returning the signature bytes. Not complicated at all. Okay, and this here, since we just returned this here I can make it easy for myself and basically do this again. So I'm just saying, and this sending signer has been invoked, and I return 789 as signature. And I don't just this as signature bytes because we don't need to map it. Yeah, here's just the signatures. So it's not the actual signatures in the sense of the signatures I created, but I'm returning the signatures of the transaction. So the fee payer's signature, right? Does that make sense? So basically, it's not async. There we go. So wait, just first I show you. So wait, I don't have a sending signer yet. Let's add a sending signer. Sending signer. Send 6. And then I'll add the sending signer somewhere here in the middle because it doesn't matter where it is. This will sort it accordingly. Hold on. No, this will actually not do anything. Here, if I just partially sign, it will ignore my sending signer. So this is the same as before. Only if I allow it to actually send, if I await send, what was it called? Sign and send transaction with message signers for my transaction message. Then it's gonna also fail. No! Ha! This doesn't fail because I'm not calling the sign transaction with signers. This one would make sure that I have a sendable transaction that has all the signatures. But this one, the sign and send, doesn't make sure that I have all the signatures because it will never get all the signatures. It can't check all the signatures because there is a sending signer in there as well. So it can't check that all the signatures are present, so it will just work. That's funny. Anyway, so if I partially sign, then I get this, right? Then I have this from before with the modifying signer and the partial signer's signatures added. And then if I add the sending signer, so if I call it the sign and send, then this signature is returned. But really, I think that's wrong. I mean, because what that should return, what I would expect that to return is the signature of the actual transaction. So I would expect that to be the fee payer's signature. So with this signature that I can then, find the transaction. So my implementation here, this is actually wrong. I shouldn't return this in here. I should set the signature in my transaction before I send it. But then what I return should be the get signature from transaction of this transaction. So here we have a signature and here we have signature bytes. Wait, that's already the string type then, right? Okay, so then it's probably, how do I get that? Signature. That's why this is a map. The dictionary is just, we have the addresses and the signatures, and the map is also sorted with the fee payer's signature first, I think. So something like this, a map between addresses of a transaction and the signature bytes. Wait, then a message bytes, but I can't get the fee payer out of there. How do I get the... Can I see the implementation of this? Given a transaction signed by its fee payer, this method will return the signature that uniquely identifies it. And that's the string, but I want the signature byte. Let's look at it here then. There we go. Get signature from transaction. Transaction.signatures. So the signature map somehow does seem to have an order though, as I said. Because we get index 0. Dictionary and map are largely interchangeable terms. Damn it. Both are collections that store key value pairs. Map, order. It preserves the insertion order. Dictionary, the order of keys is not guaranteed. There we go. That's the difference that I make up. Good enough. So the map has an order and the first one in order is the fee payer. So I can get the first transaction signature, and then this one decodes it, but I don't want to do that, so I'm just going to do this. So in my wonderful sending signer, I'm going to get the transaction signatures first. And that's what I will return. That's the map. Or null is not assignable to. Okay, this could be null now. Fair point. Here I can assert that it has all the signatures, because I would need to assert that here anyway before sending, but I'm just gonna assume that I have it. So this will be fine for now. And then it will return the one of this guy, because this is the fee payer. So if we do it now, then the sign, what? It's returning the signature of the modifying signer now. That's weird. Yeah, the first in this list is the modifying signer. So that's still bad. That's not what I want. I still want the fee payer. At least that's what I, like, I'm also not 100% sure, but I would assume that's what I need to return here. The signature bytes. Or maybe that's even my mistake, because my modifying signer is doing something that it shouldn't do. Because here I basically force it to use this as signature map. Maybe here I'm already making the mistake. This should not be in this order. You know what? Just for testing purposes, instead of this modifying signer, I'm gonna generate a key pair signer, which is also a partial signer though, I think. Is a key pair signer a partial signer? Probably. Yep, key pair signer is a partial signer. Do you have an example for a modifying signer? But also, wait, let's do test with this guy. This should all run in parallel, and I'm just gonna let mine wait 1 second or half a second, at least half a second, such that this one is definitely signed first. Let's check what happens then. This is still a dictionary now, right? Here it's in the other direction now. This is a dictionary, so this is sorted by name of the address. So what if my address would start differently? Now then this still would be on top. Interesting. The rest seems to be in random order, or not random, but you know, depending what that address is. Here it starts with 7, so that's before the A, but the Z is still on number 1 spot. This one is always the first one. The others, then it's basically sorted alphabetically, yeah, depending on which that address is. But this one is always the first, the fee payer. Call it fee payee. Fee. So no matter what I call it, this one is always on top. So probably when I was doing the modifying sign, I messed something up, because when I'm doing the modifying sign, oh shit, what did I do now? Attempting to sign a transaction with an address that it is not a signer for? What? Expected address, unexpected address. What? What's happening here now? We're modifying, we invoked the modifying signer for this guy. Let me try that again. Yeah. Attempt to sign a transaction with an address that is not a signer for it. Signer 5 and signer 6. They should all be signers though. 4, 5 and 6 should all be signers. If I don't have signer 6 in here, then it works again, but it 1, 2, 3, 4, 5. But it overwrites that part. Maybe that's the issue. What if I put signer 6 in there again? That's the signer 6 is the key pair signer. Yeah. Then it complains that sign, modifying, and partial transaction signers. Partially signed transaction with signers. Calls the sign calls the partially signed transaction. So let me quickly check. If I'm not adding a signature, if I'm not adding this signature, then I'm also not getting that problem. Ha! And then it's also in the right order again. Okay, so my implementation messed with the map. So that was my issue. The fee payer should still be at the first spot here. And then also that implementation is correct, you know, getting the first one as the fee payer signature, which it can then be identified with this one. And here the modifying signer added null. If I wanted to add a signature for this guy, can I somehow fix my implementation? I would probably need to flatten this and just change the address and keep the rest the same. Maybe like this. Yeah, that looks better. Look, then I can change the signature of the modifying signer. So this is the result after. Wait, let me make this bigger. This is the result after the partial sign. The partial sign signs all of them except for the sending signer, but the fee payer is still in the first spot. And then if I send and sign, then it also signs for the sending signer and returns the first signature. So the fee payer signature, not the sending signer signature, the fee payer signature. I think. I'm relatively sure that that's what should happen. But then again, I don't really see that in the docs anywhere. But that's the only thing that makes sense really, because we just return one signature bytes for each transaction. I'm assuming it's the fee payer signature. That's the only thing that makes sense in my eyes. Because the app is not interested in the actual signature that we just need to provide to the transaction before we send it, and then we send it and we give the signature, so the identifying element, back to the application. And with that signature, not necessarily my signature of the sending signer, but just the signature identifying that transaction. We could call this the transaction ID. So we return the transaction ID, which happens to be the fee payer signature. That's what we return here. Because with this transaction ID, the fee payer signature, we can confirm that transaction and query the state and everything. Okay, I think that's good enough for a deep dive on signers. I think you get it now. We have had a look at the different types of signers. Obviously, you will never or rarely ever implement a signer yourself. I just did it for fun today to understand that part as well. You will just add them here when you create the messages and call the send and sign, or just a partial sign, or a fully sign. So the, what's it called? The sign transaction message with signer, not just partially, because the sign transaction with signers makes sure that all the signatures are present. Yeah, and that, I think, is good enough for me. I learned something. We got a better understanding of this. Really nice docs. Check out those docs if you want to learn about the kit. You can learn about transactions, how to build them properly. And yeah, I would say that's good enough for today. We had a closer look at the kit. I love the kit. You really want to work with the kit if you do JavaScript, because it's the better JavaScript SDK than the Web3.js. It's just nice. It just handles that stuff for you. You can just provide the signers and it will take care that they're used in the right order, and just you don't need to worry about those things. It's really nice. But in order to be able to use that, you need to understand what's actually happening there. And that's why we had to do such a deep dive. Now we understand the signers of the Solana kit. And with that, I shall leave you. You can watch those videos. Here's a whole playlist on the kit. Subscribe if you haven't already. Give me a like. And then I'll see you in the next deep dive of the kit or anything else Solana development related. Till then, peace out.